Hello students, welcome you all. Now in this lecture, I will tell you the details of electrocyclic reactions. In my previous lectures, I told you about the main features of pericyclic reactions, classification, the brief of classification of pericyclic reaction, and how to construct the pi molecular orbital diagram for even carbon systems like this conjugated pi systems and odd carbon systems, that is the allylic system. Now today I will tell you the main selection rule for this electrocyclic reaction. How can we arrive at the selection rule or the rule for the electrocyclic reactions? So what I told you about this electrocyclic reaction, we can define the electrocyclic reaction as the ring opening or ring closing reaction which occur at the expense of one pi bond. So these are ring opening or ring closing reaction. Which occur with the expense of one pi bond. Okay, so simplest example, if you will take the simplest example, if we have butadiene system, then it may undergo ring closing reaction in presence of either heat or light. So the cyclic shift of electron will start on taking the energy. By taking the energy, cyclic shift of electron will start, and that will be converted into cyclobutene. Okay, so if you will see here, number of pi bond is 2, and here the number of pi bond is 1, and one new sigma bond is formed, and number of pi bond is decreased by 1, plus one new sigma bond is formed, plus one ring is formed. Okay, so this may occur in a backward direction, that is ring opening can also occur. Ring opening can also occur like this. Okay, so this is one of the simplest example for the electrocyclic reaction. Now in the same way, we may write the this ring opening ring closing reaction for the hexadiene, for the hexatriene, and hexatriene that would be converted into cyclohexadiene, and so on. Okay, so how can we get the selection rule for the electrocyclic reaction that you will see here? Now before coming to that one, we should before discussing these the detail of electrocyclic reaction, I should tell you the two terms which comes in electrocyclic reaction. One is called as the conrotation and another is called as the disrotation. Two terms, these are very much important, and you should try to understand these two terms. So one term is called as a conrotation of the orbital. Conrotation. So what is this conrotation? When both the orbitals, because two orbitals are involved in bond formation, okay, or bond breaking, two orbitals are involved. So we are talking about the two orbitals only. We are talking about only two orbitals. So when both the orbital, we can write when both the orbital rotates in the same direction, when both the orbitals rotates in same, both the orbital means, or we can say either it may be sigma orbital or pi orbital. Both the orbitals means either you may take both sigma orbital or pi orbital. when both the orbitals rotate in same direction, then such type of rotation of orbital, such type of movement of orbital is called as the conrotation. That is called as the conrotation. Okay, so this rotation should be in same direction, and that can be either in a clockwise, two orbitals can rotate, or both orbitals can rotate in a clockwise direction or anti-clockwise direction. So that is either clockwise or anti-clockwise. Clockwise. Okay, so like this, either clockwise direction or anti-clockwise direction. So suppose if you have the sigma orbital, so suppose I write that bond is formed between the two sigma orbital. Okay, so here this is sigma orbital is involved, and suppose this sigma orbital breaks. Suppose this sigma orbital breaks. So here this bond is formed is the sigma bond, and suppose these two the sigma orbitals break. Then suppose this is plus plus and minus minus. If bond is formed, then no doubt this lobe should have the middle lobe should have the plus plus sign. So in this case, how during conrotation, these two lobes, these two orbitals that will move in the same direction. If this is moving in the same direction, then this lobe or this orbital will move also in the same direction. So if this lobe moves in this anti-clockwise direction, this is also moving in anti-clockwise direction, then this lobe will move like this. So anti-clockwise rotation of this, in the same way anti-clockwise direction of this orbital. So this is anti-clockwise. In the same way, this may rotate in a clockwise also. It may rotate in a clockwise manner also. It may rotate in a clockwise manner also, either this one or this one. So minus, plus, plus, minus. Okay, so either it may rotate in this direction. Okay, this is clockwise manner. This is clockwise manner. So this is anti-clockwise rotation. Both orbitals move in an anti-clockwise manner, and this is the clockwise manner. So if this lobes move in this direction, then this will be like this. So clockwise. In the same way, if like this, it will go over here. Okay. So when bond break, then when bond break, what will happen? So what will happen? So suppose after breaking the bond, then this orbital, this sigma orbital, that would be converted into the p orbital. When the bond breaks, suppose then in that case this will come up. Okay, negative charge will come up, or suppose. So this is the way when the sigma bond breaks. Okay, when the sigma bond breaks. In the same way, we can understand for the p orbital. We may understand for the p orbital. Suppose these two p orbitals are there, which are involved in the formation of pi bond. Suppose these two orbitals, one and the, if these two orbitals are involved in a pi bond, then it may undergo ring formation reaction. Okay, it may undergo ring formation reaction. Suppose. So pi overlap will occur. This is pi overlap. So plus plus, minus minus. Okay, so when it moves in a opposite direction, suppose I move in a clockwise, suppose anti-clockwise direction. So both orbital during conrotation, both the orbital move in the same direction. So this orbitals move here, this also moves in a clockwise direction. So if this moves here, then this will go over here like this. In the same way, this will go over here. So this is our clockwise rotation of two orbitals. This is clockwise rotation of two orbitals, and this will be anti-clockwise rotation of two orbitals. So this is anti-clockwise rotation. This is anti-clockwise rotation like this. So this is anti-clockwise rotation. Okay. So this is called as the conrotation. This is called as the conrotation. Now, what is disrotation? Disrotation is just opposite of it. So disrotation, if you will see, disrotation. So how can you understand this disrotation? Disrotation when both orbital, either sigma orbital or pi orbital, rotate in a different direction. So when both orbitals, either sigma orbital or pi orbitals rotate or moves in different direction. Okay, then that is called as, it means one clockwise and other anti-clockwise, vice versa. So here both are moving clockwise, either both moves clockwise, both clockwise or both anti-clockwise, either both clockwise or both anti-clockwise. We may write here one moves in a clockwise. If one moves in a clockwise direction, then other will move in a anti-clockwise. One will move in a clockwise, other will move in a anti-clockwise. One moves in a clockwise, that this should move in an anti-clockwise way. So one moves in clockwise and other moves in anti-clockwise, and other moves in anti-clockwise manner. Okay, this is called as the disrotation. This is called as disrotation. Now, if you will see the example of this disrotation, then suppose in this case for sigma orbital, this is plus minus. So if one moves in an anti-clockwise manner, this will move in a clockwise manner like this. This is anti-clockwise, this is clockwise. So this lobe will come here and this lobe will go over here. So this is one clockwise, another anti-clockwise, or another way that you may represent so if this is moving in this direction, then this will also be like this. As you can see, this lobe is moving in this orbital is moving in a clockwise, this is in anti-clockwise. Here this is anti-clockwise, this is clockwise. In the same way for p orbital, this is for sigma orbital movement. For p orbital you may move, you may show like this. So if one is in anti-clockwise, another is in clockwise like this. So one is anti-clockwise, another clockwise, or you may show like this. So this is moving in a anti-clockwise and this is moving in a clockwise. So this is called as the conrotation and disrotation. So these are the two terms that we should clear when we start this electrocyclic reaction. Now, in electrocyclic reaction, another thing that we should remember in electrocyclic reaction, when conrotation occur, during conrotation of the orbital, which symmetry is maintained? Which symmetry is maintained? Suppose suppose I write I have written the only this orbital. I have not written the pi bond over here. I have only written the this is sigma orbital for this is cyclobutene. So suppose if this the rotation occur in a conrotation way. So what will happen? So conrotation means the orbital move in a both orbital move in a same direction, either in a clockwise or in a anti-clockwise. So this if moves in a this direction clockwise, then this should also move in a clockwise. It means this will come here and this will go down. So what you will get? What you will get? You will get here. So the bond will break, this bond will break, and this minus lobe, small lobe means minus charge will come up and plus charge will come down. So what you can show, this minus is coming up and this plus is coming down, and here if you will see, plus is coming up and minus is coming down. So this is the conrotation of the orbital. This is conrotation of these orbitals. Okay. Now if you will do the disrotation of the orbital, so let me rotate in a different direction. Sorry, let me rotate in a different direction. So if the disrotation of orbital takes place, that is, if they rotate in a different direction, means the bond opens in this way. So one is moving in a clockwise, another is moving in a anti-clockwise. So if this is going up, then this lobe will come down. So this is clockwise manner, and this is in anti-clockwise manner. This will go up, this is going down. So what you will see after when this bond breaks, then that would be converted into p orbital. So this sigma orbitals, that would be converted into p orbital, and this plus sign is going up. Plus sign is going up. Minus sign is coming down. This plus is coming up, and this minus is coming down. This minus is coming down. So this is disrotation. This is conrotation. Now what we have observed here, now if you will see the symmetry, and if we see the mirror plane symmetry, then if you pass the mirror plane like this, then in front of plus you will see plus. In case of reactant orbital, these are the reactant orbital and these are the product orbital. So what I told, the main feature of the pericyclic reaction in my in my first lecture, introduction lecture, that the reactant orbital and product orbital should have the same symmetry. Either it may have the mirror plane symmetry or it may have the C2 symmetry. So if you will see here, and if you will pass the mirror plane, so let's see for the sigma symmetry, that is mirror plane. If we pass the mirror plane, then what you will see, it has the mirror plane. It has the mirror plane. Now if you pass the mirror plane here, then in front of minus you will see the plus. So that's, or in plus lower lobe plus, and this is minus. So it doesn't have the mirror plane symmetry. It has mirror plane symmetry, but it doesn't have the mirror plane symmetry. It means the symmetry is not conserved during the reaction. The symmetry is not conserved over here. So that's why. Now let's see for the next, that is C2. What I told you, in pericyclic reactions, in electrocyclic reactions, we are concerned with two types of symmetry. One is the mirror plane symmetry, another is the C2 symmetry. So here there is mirror plane symmetry, but here no mirror plane symmetry. Now let's see for C2 symmetry, whether C2 symmetry is there or not. So if I pass the one rotation axis and rotate it by 180 degree, then what you will see, after rotating, this minus will go over here and this minus will go over here, and this at the place of this plus will go over here and this plus will go over here. Means at plus is coming, at minus is coming, and you will get the same orbital. Yeah, no change will occur. It means it has C2 symmetry. It has C2 symmetry. Now let's see here whether it has a C2 symmetry. Rotate it by 180 degree, and what will happen after rotation? What will happen? This point will come over here and this point will come over here. This lobe will go over here. This lobe will go over here. So what you will see, this lobe will go over here and this lobe will go over here. Means at minus is coming, at plus is coming. So that's why this has C2 symmetry. Means during conrotation, which symmetry is maintained in reactant and product? Which symmetry is maintained? So mirror plane symmetry was not maintained, the C2 is maintained. So for conrotation, C2 symmetry is maintained in reactant as well as in product. Okay, so here C2 is maintained, while conrotation C2 is maintained. This is very important point that we should remember. C2 is maintained over here. So we can understand it with the help of this model also. If you will see this model, okay. So let me show you this model. So if this is the bond, this is the positive lobe, and this is the negative lobe. This is the model for this cyclobutane system, and suppose this is the sigma bond which is formed. This is the sigma bond which is formed, and this is positive lobe, this is the negative lobe. Now suppose if you do the conrotation means you are moving it in the same direction. Both lobe will move in the same direction. If this lobe move in this direction, means here it is moving in this direction, then this will also move in this direction. Okay, so what we have to do, I have to rotate in the same direction. So if both are moving in the same direction like this, and what you will find the plus at one side, minus, and at other side plus. Okay, so again you can see it again. Suppose this is the sigma bond which was present. This was the sigma bond which was present, and rotate it by 180. Rotate in a conrotation. Conrotation, we have to do the conrotation means both lobes should move in a same direction. So this in this direction, and this also moves in this direction. So what you see, this is positive is up, and for here the positive is down. So one side positive is up and positive is down. Okay, so this is called as the ring opening reaction, and during this ring opening reaction you will not see the mirror plane. If you have the mirror plane, in this case you will not, the mirror plane is not there in between this, while the C2 is there. So C2 is there but mirror plane is not there. So C2 is there in the reactant as well as product. C2 is here in this way, C2 is here, and also C2 is also present over here. Okay, but mirror plane is not present. So in this way we may understand it with the help of model, how C2 is maintained while the ring opening reaction in this case. Now in the same way, when you will do the disrotation, suppose if you are doing the disrotation, what you have seen during disrotation, which symmetry is maintained, if you will see, then here during disrotation, if you pass the mirror plane, and in front of plus you will have plus, in front of minus you will have the minus. So here sigma is present. Okay, it is symmetric with respect to sigma. Now let's come to the orbital of product. So if you will pass the mirror plane here, then what you will see, you will plus, in front of plus is there, in front of minus is there. Okay, so that means it also has the mirror plane. So Means when we do the disrotation, when both are moving in a different direction, then we will have the mirror plane symmetry. So during disrotation, sigma is maintained. Sigma is maintained. This is very important point. Sigma is maintained during disrotation. So we may also understand it, how we can do the disrotation. Suppose this is the sigma bond which is present. This is the sigma bond which is present, and disrotation means both moves in a opposite direction. This is moving here and this also moves here like this, and you will see, you will find this one both positive are up, or both positive may be down. So this has the mirror plane, this has the mirror plane. In front of plus would be there, and this, the reactant orbital is also having the mirror plane. Reactant orbital is also having the mirror plane. So like this we may understand it. So the final conclusion that we have seen, what are the conrotation? When orbital move in a same direction. What are disrotation? What is disrotation? When both orbital move in a different direction. During conrotation, C2 is maintained. During disrotation, sigma is maintained. So this we should be very much clear. Now let's see the selection rule. How we may arrive at the selection rule for the electrocyclic system. So now let's see the selection rule for the electrocyclic reaction. So how we can arrive at the selection rule? Selection. Now in electrocyclic reaction or cycloaddition reaction, or we will see the sigma-tropic reaction, so we will see two type of system. One would be the 4n electron system, another would be the 4n plus 2 electron system. So first I will tell you the 4n electron system. 4n electron system. Okay, so like this butadiene is a 4n electron system, and it may be 0 or 1 2. So if you put 0, not for 0, for 4n plus 2 electron system we may put n is equal to 0, but for here either n may be equal to 1, 2 or 3, and we may write n 1, 2 and 3, so on. So this is our 4n electron system, and in the same way if you draw for cycloocta, this is also the 8 electron system. 8 pi electrons are present over here, so this is also 4n electron system. Whereas hexadiene, or this hexatriene, so this hexatriene, this is 4n plus 2 electron system. This is 4n plus 2 electron system. So we will see two type of system. One is 4n electron system, another is the 4n plus 2 electron system. Now for example, if we have butadiene, or when this cyclobutene converts into the butadiene, or I should take the substituted cyclobutene. If this is methyl hydrogen, this is methyl, this is our hydrogen. Okay, so in this case, when heat is passed, so either what I told you, the pericyclic reaction, it occurs in presence of heat or light. So in presence for this system, when heat is passed through this system, then the product obtained in this case was something like this. Experimental, this is the experimental result. The product obtained was, this was the product obtained. Okay, either this product or either we may get this product. But out of this two product, so these two CH3 groups are quite close and statically hindered. That's why this is disfavored. So this product is disfavored, whereas this product is favored. This product is favored. So this is the result under thermal condition. So this is the result under thermal condition. Okay. So how, if we see the mechanism, under what mechanism we may get this product? So what should be the mechanism so that we arrive at this product? So what is the name of this one? If you will see the name, this is trans. This is the trans. CH3 is up, CH3 is down. And if you want to name it, then this is first, second, this is third carbon, fourth carbon, like this. And then third and fourth, two trans methyl group is present. So 3,4 trans. What we can write? This is trans 3,4 dimethyl cyclobutene. And what is the name for this? If you want to write the name for this, then this is 1, 2, 3, 4, 5, 6. 6 longest carbon chain has the 6th carbon. So if you write, then this is first, second, third, fourth, fifth, and this is your 6th. Okay. Now at second and third, this is the double bond, and 4 and 5 double bond is present. So this is our this double bond is here. If we want to give the nomenclature, then this is E, because two higher priority group. This is CH3 is the higher priority group, and this is the higher priority group. Okay, well, hydrogen is present over here. So these two lower priority group are on the opposite side, or two highest priority group are on the opposite side. This CH3 and this is the two highest priority group. These two highest priority group are on the opposite side. That's why it is E. In the same way, here also, if you see this 4-5 bond, then this one and this one, two highest priority group are on the opposite side. That's why it is also E. So what name we can give? We may give, this is 6 carbon chain, and at second and fourth position double bond is present, and at second, so this is what we may write, it is 2E. Okay, 2E, 4E. This is 2E, 4E. Okay, 2E, 4E. So 2E, 4E hexa 1,2,4-diene, and here this is Z. This is also Z, because two highest priority group are on the same side along this double bond, and along this double bond also two highest priority group are on the same side. So this would be 2Z, 4Z. This is 2Z, 4Z hexa 1,2,4-diene. Okay. Like this. So how can we arrive at this result? If you see the mechanism for this, if you want to see the mechanism, then how can we arrive at this mechanism? So this can only be obtained, this result can only be obtained when here the ring opens, if the ring opens in a conrotation manner. So this is ring opening reaction, this is ring opening reaction, and this can only be obtained if the ring opens in a conrotation manner. So let's see here. So if I draw the orbitals, over here, so this is plus, plus, minus, minus, and I have only drawn this sigma orbital, I am not drawing the pi orbital, and this is our CH3, and this is the H, this is H, this is CH3. Okay. Now let's move this in a conrotation manner, means when both the lobe moves in a same direction. When both lobe moves in a same direction, it means suppose both lobes are moving in a this anti-clockwise manner. This is moving this way. Okay. Suppose this moves in this way. Suppose. This is moving in a clockwise manner, so this should also move in a clockwise manner. This should also move in a clockwise manner. So what you will obtain? You will obtain this bond will break, and this lobe that would be converted into p orbital. So this plus is coming down, minus is coming up. In this lobe, this plus is coming up and minus is coming down. Okay. Now when these lobes move, then no doubt this substituent over this carbon will also move. So substituent should also move. So this CH3 will also move. CH3 moves in a clockwise manner, and it will go in, whereas hydrogen is also moving in a clockwise manner. Hydrogen is going out. So CH3 is coming in, and hydrogen is coming out, like this. And for this one, hydrogen is coming out because hydrogen will also move in a clockwise manner. So hydrogen is coming out and CH3 is coming in. So this is one of the result. This is one of the result when lobes are moving in a clockwise manner, same direction. So I have done the conrotation. And here how this is result is obtained when lobes are moving in a clockwise. So clockwise rotation. When we rotate in an anti-clockwise manner, if you will rotate in an anti-clockwise manner, then what will happen? Let me rotate in an anti-clockwise manner. So if we will rotate in an anti-clockwise manner, then this will move over here and this will move over here, and in the same way this will move over here and this will move like this. So what will you obtain? You will obtain, so for this, see this lobe, plus will come up, minus will go down. Plus come up, minus go down, and here minus come up, plus go down. Minus come up, plus go down. And if you see the substituent, then substituent is going out, hydrogen is going down, hydrogen going in, CH3 is coming outside, hydrogen is going inward. So CH3 is coming outside and hydrogen is going inward. Here, what about this substituent? Hydrogen is going in and CH3 is going outside. So hydrogen is going in, CH3 is going outside. Okay, so this is the result when we are moving in an anti-clockwise manner. And this will be your major product and this would be the minor product. So how we can get this result? We can get this result only when the lobes and substituents are moving in a anti-clockwise manner. And lobes and moving are in an anti-clockwise manner. So which symmetry is maintained over here? So during Conrotation, what I have told you, during conrotation, the C2 symmetry is maintained. So whether the C2 is maintained or not, C2 is maintained when conrotation occurs, I told you. So if you will see here, this has C2 symmetry and this also has the C2 symmetry. If you will pass the rotation axis and if you rotate it by 180 degree, then this plus will go over here and plus will go at the place of plus, minus will go at the place of minus, CH3 will go at the place of CH3, hydrogen will go at the place of hydrogen. So that's why C2, here C2 is maintained, here C2 is maintained. So in reactant and product, the symmetry is conserved. So this should be the mechanism for this. This should be the mechanism for this. So what you have seen? You have seen that under thermal condition, when for 4n electron system under thermal condition, it will undergo the orbitals will move in a conrotatory fashion. Now same for suppose for disrotation. So let's see what should be the result when disrotation occurs. Or suppose, so this was the result when heat was passed. This was the result when heat was passed. Now suppose I take it when under photochemical condition. So second case, photochemical condition. So what was seen experimentally, what was seen under photochemical condition, the product obtained was, this was the product obtained under photochemical condition. This was the product obtained under photochemical condition. Either this or this, and both are equivalent. Both are equivalent. Either this product or this product was obtained. So what should be the mechanism? What should be the mechanism so that we obtain this product? The mechanism, if you will write, this product can only be obtained when orbitals undergo disrotation. When orbitals undergo disrotation, then only such product can be obtained. Then only such product can be obtained. Okay. So let me move in disrotatory manner in a different direction. So both lobes moves in a opposite direction. So no doubt here, so hydrogen will come outside, CH3 will go in. Here the CH3 is going outside, hydrogen is going in. So the product obtained, that would be, so plus is going up, minus is coming down. In this lobe, plus is going up, minus is coming down. So in both the lobe, plus is up, minus is down. And here CH3 is coming outside and hydrogen is coming inside. In the same way, here hydrogen is coming outside and CH3 is coming inside. Okay, so this was the, so such product, so this is a product which is only obtained when disrotation of orbital occur, and during disrotation you can see the mirror plane symmetry is maintained. Sigma is both in reactant and product, sigma is maintained. So what you have seen for 4n electron system, when disrotation of orbital occur, under this can only occur under the photochemical condition, and conrotation of orbital only occur under the under the thermal condition. So this can be understood with the help of model. So we have substituted cyclobutene or trans-substituted cyclobutene. Here methyl group is above and another methyl group is below. Okay. So let me rotate in a disrotatory manner, or we can rotate in a conrotatory manner. So when see this model here, this is the bond which will break, or this is the sigma orbital which will break, and this is the trans position. So here methyl group is above and here the methyl group is below. This hydrogen is above, this hydrogen is below. So this is trans 3,4 dimethyl cyclobutene. Now when it will undergo disrotatory manner, so when the orbital moves in a disrotatory manner, that is both orbital will move in an opposite direction. Suppose one is moving in this direction, okay, so this methyl group is coming inside and this is moving also in opposite direction. You can see this methyl group is going outside. So when you do the disrotatory, when the orbitals move in a opposite direction, one methyl is going in, another methyl is going out. So one methyl is going in, another methyl is going out. So this is the case when disrotatory motion of the orbital takes place, and this only takes place under the photochemical condition. Under thermal condition, what I told you, the product was when both the methyl group was inside either or both methyl group was outside. So two products was obtained under thermal condition. So this is the photochemical condition. In previous condition, the thermal condition, the methyl group, either both methyl group will outside or both methyl group will be inside. So this happens, suppose this is the model and this is trans 3,4 dimethyl cyclobutene, trans 3,4 dimethyl cyclobutene. Now if we rotate both orbitals are rotated in the same direction. So this orbital is rotated like this and this is also rotated in this direction. So what do you see? You see both the methyl group is going outside. Both methyl group is going outside. Or suppose if you rotate in this direction, suppose this is moving like this and this is also moving like this. And what you see? You see this two methyl group is coming, both methyl group is coming inward, and when both methyl group is coming inward, the product is sterically hindered. So this type of product is not favored. Which product is favored? When both orbital move like this. This is going here, this is going here, and you see both methyl group is outside. So in this way we may understand the conrotatory motion or disrotatory motion when we have the substituted cyclobutene. Now this is for foreign electron system. So for foreign electron system, what you saw? For foreign electron system, what you saw the rule. So let me write the rule for foreign electron system. So we should see for foreign electron system, and we will see for foreign plus 2 electron system also. So under thermal condition we have seen, and under photochemical condition we have seen. So under photochemical condition, what kind of motion of orbital? Orbitals are rotating in a disrotatory manner. So for foreign electron system under photochemical condition, orbitals are rotating in a disrotatory manner. Whereas what we saw earlier, under thermal conditions, orbitals move in a conrotatory fashion, so that we get the required product. So this is the rule for foreign electron system. Now let me understand you now the foreign plus 2 electron system. Okay, so I will now discuss the foreign plus 2 electron system. So now part B, 4n plus 2 electron system. Okay, now first we will see under thermal condition. Okay, So 4n plus 2 electron system here, n is equal to either 0, 1, 2 and so on. So if I take cyclohexadiene, if I take substituted cyclohexadiene, so this is suppose methyl and this is hydrogen, this is methyl and this is hydrogen. Now under thermal condition, experimentally it was seen under thermal condition the product obtained was this. So here this bond will break, this bond will break, it will come over here, this will go over here and this will. So this bond will break, the sigma bond will break and the product obtained was, this was the product. So this was the product, and in this case under thermal condition so what we have seen that this methyl group under thermal condition, one methyl group is going outside and another methyl group is going inside, either this product or you may write when the orbitals move in a different direction, then you can see the product. So one methyl group is going outside, another methyl group is going inside. Okay, so if you if we will see the mechanism of this, so such type of product will only obtained when these orbitals will undergo disrotatory manner. So let's see. Let me draw now orbitals. So I am not drawing this pi bond here. I have drawn this orbital here. So this is the sigma bond and this is your methyl group, hydrogen, methyl. Okay, so let me rotate. So this product, such type of product will only obtained when the orbitals will undergo disrotatory motion. So disrotatory motion means they will move in a opposite direction. So let me move this in opposite direction. So this orbital moves suppose in an anti-clockwise manner, this moves in a clockwise manner. So if this moves in a clockwise manner, hydrogen will also move in a clockwise manner, this lobe will also move in a clockwise manner, and this methyl group will also move in a clockwise manner. So as you can see, this methyl group, when this orbital moves in a clockwise manner, then methyl group is going in and hydrogen is going outside. So methyl is going in, hydrogen is going outside. In the same way, when this rotates in a anti-clockwise manner, this lobe, when this p orbital rotates in an anti-clockwise manner, then methyl group is going outside and this lobe comes here, and here I should write the hydrogen. Okay, so the hydrogen will move in. So methyl is going out, hydrogen is going in. Here the methyl is going in, hydrogen is going out. So the product obtained, so what should be the product? So product should be now here this positive lobe will come up, negative lobe is coming down. Here in this case positive lobe is going up, negative lobe is coming down. Okay, so now this methyl group substituent, this methyl group is coming outside and this hydrogen is coming inside, whereas this methyl group is going inside and hydrogen is going outside. Okay, so under disrotation you can get this product. Or if in a opposite direction, suppose this moves in a anti-clockwise, this moves in a clockwise, then you will get this product. So such type of rotation will only occur under the thermal condition. We are only concerned with the symmetry of this orbital. So here this orbital, if you will see, it is symmetric with respect to the mirror plane. I am only concerned with the symmetry of orbital, not the symmetry of substituent. Here also these orbitals, if you will see these orbitals, then this is symmetric with respect to the sigma. So this is also symmetric. So during this rotation, what I told you, during this rotation, sigma is maintained. Okay, sigma is maintained in sigma symmetry is maintained in reactant and in product. So this is about the thermal condition. So what you have seen in a thermal condition? In thermal condition, for 4n+2 electron system, under thermal condition, what kind of rotation of orbital takes place? Disrotation of orbitals takes place under the thermal condition. Disrotation of orbitals. Now let me understand you under photochemical condition. Okay, so under photochemical condition, what would be the product under photochemical condition? So experimentally, so under photochemical condition, the product obtained was, this was the product which was obtained under photochemical condition, when both the methyl group is going outside. Either this product or you will obtain this product. So experimentally this product was seen. So as you can see, this is strictly hindered product. So this is disfavored and this is favored one. Now, so such product can only be obtained when the orbitals undergo conrotatory motion. So if you will see the orbital motion, under conrotatory motion, what will happen? Both orbital will move in a same direction. So if this is moving like this, then and this will also move in a same direction. So this methyl group will come in and this will go down, hydrogen will go outside, and here this methyl is going outside, this lobe will come down, okay, and this lobe will come up, hydrogen will go in like this. So the product obtained so positive lobe is coming up, negative lobe is coming down. Here negative lobe is coming up and positive lobe is coming down. Okay, what about this substituent? This methyl substituent is going outside and here this methyl substituent is going inside. This methyl substituent is going inside, hydrogen is going outside here, and here the hydrogen is going inside. So either this product would be obtained or or you will see either you will get this product. Okay, so what we have seen, so under photochemical condition for 4n plus 2 electron system, the rotation of orbitals for 4n plus 2 electron system under photochemical condition, the rotation of orbital that would be conrotation. So orbitals will move in a conrotatory manner. So this is our rule. This is our rule for the electrocyclic system. So we should remember this rule for electrocyclic system when we will solve the problem. Okay, so this is about the selection rule for the electrocyclic system, and now in my next lecture we will analyze this rule by the different method. So different methods, for example, orbital symmetry correlation method or frontier molecular orbital method, that is called as the FMO, or we will understand it with the help of the Huckel-Mobius method. Okay, thank you.